cats for a little while. But what was the last thing we were discussing? Anybody? Convolutional neural networks. So a quick recap. This is what we said. That pattern classification tasks like, does this picture contain a cat? Or does this recording contain the word hello? Can be performed by scanning the input. And scanning was performed using, the act of scanning is essentially an act of convolution. And so scanning could be performed using convolutional neural networks. For two-dimensional or higher dimensional scans, we call it a connet or a convolutional network. For one-dimensional scans, for like in the case of speech, we called it a time delay neural networks. So the scanning itself is equivalent to scanning the input with an entire network was equivalent to scanning the input hierarchically with the individual neurons and combining the scanned maps in the appropriate manner. And if properly distributed, the lowest level neurons would capture basic patterns, and the higher level neurons would capture patterns of patterns. Each of these creates a map of the input that subsequent neurons work on. So we saw this yesterday. Now, before we continue, we saw, or in the last class, we got a basic idea of how the entire structure works. So today we'll get into the mechanics of it, but before that, where exactly did this structure originally come from? When the structure was originally proposed, it didn't start off with saying, I can scan the input for patterns and I can reorganize the scanning in different ways. The original motivation was biological. It starts with trying to interpret how human beings and other animals see. So the story goes back quite some ways. Now, initially, when people tried to understand vision, most of the early research was based on behavioral studies. How do people respond to visual inputs? How do animals respond to visual inputs? They would study illusions or things like Gestalt. You guys must be familiar with these pictures, right? How many of you actually see a cube in the top left corner? It's not really there, right? Do you see the panda? There is no panda. It's just a bunch of patches. So people would study how the brain tends to organize disconnected objects into connected ones, basically hallucinate various visual concepts. Yes?
Just out of curiosity, will the current network recognize the panda?
It probably would, right? So, but I'm guessing. I've never tried. Maybe there are some papers which actually discuss this. Anyway, so somewhere in the 1950s, 1959, people were sort of working on this from a phenomenological perspective. There was no real understanding of how the brain processed images. So in 1959, you had this groundbreaking paper by Hubel and Wiesel, where they studied cats. They anesthetized 24 cats, and then they immobilized them, put them on artificial respirators. They used truth serum to anesthetize them. They never actually told anybody if they killed the cats or not, but then they said, but they did report that afterwards they analyzed the brain tissue. So I'm assuming the cats didn't come to a happy end. They stuck electrodes into the cats' heads and studied the response of the striate corpus, which is out of the back of the head. And strangely enough, the way your vision works, now the human eye is a classic example of why we are the outcome of unintelligent design, right? The neurons that actually sense the eye, or sense light, lie in front of the retina, and then they fold backwards. And there's a little hole in your retina that the neurons go through to go to the brain, which is why everybody has a blind spot. That's the hole through which the neurons fold backward and go into the brain. And the first thing that happens, you'd expect that things would get processed serially backwards. It's the exact opposite. They first go to the back, and then the signals come forward. It's kind of weird. So anyway, they studied the initial the V1 neurons that actually capture the input from the eye. So here's what they did. They take these poor cats, tape them down, and tape their eyes open. So now, mind you, these are anesthetized cats, and beam lights of different wavelengths on their retina through their fully open slitted iris. What they were actually measuring was the immediate retinal response, 20 milliseconds. They'd beam lights of different patterns through the eyes and try to see exactly how the cat responded. So here's what they found. Now, different retinal areas, now any neuron responds to a pattern of inputs. So the pattern of inputs that the neuron responds to is called the receptive field of the neuron. So retinal cells have their own receptive fields, and on the retina itself, neurons tend to have somewhat circular receptive fields. But then when they studied the responses further back in the brain, they found something interesting. It turns out that for any particular neuron, you would have regions where if you had light in these regions, falling in these regions, the neuron would not respond. It basically sort of suppressed the neuron. There were other regions where if light fell, the neuron would fire. And the rest of the regions, basically the neuron had no response at all. So if you had diffuse light falling on the eye, these excitatory regions would cancel out these inhibitory regions, and there was really no response. But then when you began having very specific oriented patterns falling on the eye, here's what happens. Now, what they found was the inhibitory regions for any neuron sort of lay parallel to the excitatory regions, which means that the eye responded most to light, to lines oriented in a specific direction. Different cells responded to different lines of different orientation. So here was a typical example. They have this line being beamed into the eye, and as they rotate the line, you can see that the response of the neuron begins to increase, and this particular neuron seems to respond most to vertical lines. Now, it was not just lines. If you just took a point of light and moved it up and down and left and right and so on, the response was the same. You'd find that when the motion was in the vertical direction for this particular neuron, that's when the neuron responded most. For other directions, it didn't actually respond. So here's what they found. Oriented slits of light were the most effective stimuli for activating striate cortex neurons. And they actually found that these things, the orientation of the processing is kind of hierarchical. You have, it's not just the very first set of cells that respond. Now, because these things are sort of responding to slits, they also, to oriented patterns, the first level of cells could get confused by little spots of light. So then this got cleaned up by further processing by the next level of cells. So they call these simple S cells and complex C cells. S for simple, C for complex. And basically, both of you have these two different types of neurons. And here's how they would work. So the retinal cells would have responses like these. They're all kind of circular. But the S cell combines the responses from many retinal cells, and these retinal cells would be arranged in some pattern along some orientation. So if all of these fired, this guy would fire. And if adjacent things fired, it wouldn't. So basically, this particular S cell is going to be to respond to light of a specific orientation. But then the S cell itself tends to have it has the tendency of being confused by little spots of light. So the next level of response is done by these C cells. The C cells get responses from multiple S cells, and it's only going to fire. They only fire in response to the largest output from these S cells. So what happens is that while the S cells individually can get confused by little spots of light, and the S cells individually are sort of responsive to certain orientations of light. The C cells clean up the response. They do not get fooled by random spots. They respond to the same orientation of light as the S cell, but they're basically cleaning up the S cell response by looking at a bunch of S cells and then picking only the largest of these. So you can see where this thing is going, right? So the overall conclusion they came to was that complex C cells build their response from similarly oriented simple S cells. They basically fine-tune the response of the simple cell, because the simple cell is responsive to some orientations. The complex guys fine-tune those. And subsequent layers of neurons would sort of operate on the output of the complex cells, and they follow the same structure. So the next level of neurons would be aggregating responses of a certain set of complex cells and then cleaning them, and then you'd have more C cells cleaning them up and so on. At least this was their hypothesis. And they show that as you go down, you get more and more complex responses that are built upon simple responses. But the basic unit remains the same, that you have a set of simple cells which respond to some patterns, and then you have more complex cells which sort of clean up these responses. Now, this was back in 1959, the first time people actually studied something of this kind. And they didn't have very many laws about how you can treat animals. And so thereafter, the next set of experiments were on macaque monkeys, which were not even anesthetized. So we won't go there. Anyway, this was, but there was, these studies were kind of incomplete. And maybe they never really explained the human vision to any real extent, although they were one of the first studies of this kind. The model cannot accommodate color, spatial frequencies, many other features which neurons are tuned to. So basically, all of those cats gave their lives for nothing other than letting us build convolutional neural networks. So every time you train a convolutional neural network, it's built on the cadavers of many cats. But anyway, so this was just the biological model, right? Fast forward 21 years, 1980, and this is where the computational model begins kicking in. This is Kunihiko Fukushima. He realized that the Hubel and Wiesel model has some deficiencies. Firstly, if these patterns of neurons are actually being responsive to, if these neurons are responsive to certain patterns of input, like certain, say the earliest neurons are responsive to certain orientations, the rest of them keep building more and more complex patterns, eventually you get to a point where the combination of all of these, the complex structure that's being recognized as your grandmother. Except we know from experience that it doesn't matter whether granny is in the middle of our field of vision or whether she's off to the right, you're still going to recognize her. So we have position invariance. And so there's this thing called a grandmother cell. Has anybody heard of it? There's even something called a Jennifer neuron cell. So people who work on these things like to work on patients, epileptics. And the way epileptic patients are treated, they open up their brain and they try to fix the lesion. So they lie around in the hospital with their skull opened up. And now you have these patients lying around with the skull open, the brain exposed. And then that's when these neurophysicians scientists like to come in. They come and put a little mesh of sensors on the brain. And here's the poor guy lying in hospital waiting to get fixed, but he can't move. So then they begin doing things to him and measuring the response. And it turns out that there was a paper in Nature some time ago that in one particular patient, there was a specific neuron that only fired if he was shown pictures of Jennifer Aniston. So they call this the Jennifer Aniston neuron. There's nothing special about Jennifer Aniston. It just turns out that there are different neurons. She just happened to be the one picture they showed. But there are different neurons that actually respond to very specific patterns. So there are one or more cells in your head that very specifically respond to your grandmother. So they call them the grandmother cell. Now the point is, they can't just be one grandmother cell, right? Because regardless of the position of granny in the room, that cell's going to respond. So Fukushima's model tried to sort of overcome this deficiency. He actually came up with a computational model which looks like this. He says the visual system consists of a hierarchy of modules, each comprising a layer of S cells, standing for simple cells, named after Hubel and Wiesel's model, and followed by a layer of C cells, standing for complex cells. So here is the model. You have U0 is the retina, and then after that you have many substructures where each one feeds to the next. The first one has got a layer of C cells, then you have a layer of S cells which operate on the C cells, and then the output of the C cells go to the next layer of S cells, the output of which goes to the C cells, and so on. And each C and so the C and S and C cells occur as units, combined units. Now, only in each group, only the S cells are plastic. Only the S cells actually learn. The response of the C cells is fixed. So the S cells respond to this, and the way they are connected, each layer of S cells responds to the output of the C cells in the previous layer. And each layer of C cells responds only to the corresponding S cells. Now, even more specifically, and this is how Fukushima introduced position invariance. Within each layer of S cells, you have many planes. So this is one layer of S cells where you have many planes, and within each plane you have several cells, and all of the cells within each of these little squares have exactly the same response. The only distinction is in which region of the output of the previous layer they look at. So if you look at this guy over here, you'd have some. This is one plane of S cells. So let's say this is your image. So this guy may look at this region. This guy may look at this region. This guy may look at this region. But all of these cells have exactly the same response, meaning each of them is scanning for exactly the same pattern. And then, so you have many such groups. So the S cells in this group have one response. The S cells in this group have another response, and so on. So within each plane you have S plane, you have many types of S cells. And then following each S plane is a C plane, where the C plane behaves very similarly, except that within each C plane, each cell over here looks at a group of cells out here and picks up the largest value and copies it over. Now, he didn't actually say it was the largest value. The point was that each of these guys responds to this group of units. And it's, again, all of these have identical responses. Now, the C planes are followed. So the overall structure looks something like this. The first level of S cells looks at the retina. The next level of then the first level of C cells, each C is going to look at the output of the S cells and look at how the C cells operate. Within this little rectangle, those C cells are only looking at the corresponding rectangle in the corresponding S plane. Then when you go to the next layer, you have all of these S cells, and each of these S cells is not looking at merely just one corresponding layer, a C plane. It's actually looking at the entire combination of them. So the way it happens is if you go to the next layer over here, so you'd have all of these C cells in the first layer, and the next one you'd have an S plane, and this guy is going to look at this one over here and respond to the combination of these three. And again, you get this position invariant pattern across the entire plane, followed by another layer of C cells, which is going to just look at small regions within each S plane. So this was just the computational model that Fukushima came up with. And he even tossed in mathematical formulae to make it complete. So here is the response of the S cells. It's a very complex looking formula. I have it there just because it looks fun. But it really just looks like a ReLU. And then underneath that is the response of the C cells, which looks just as funky. But it turns out that the C cells really are just performing a max operation. They're picking up the maximum of the inputs in a small range, small group of S cells. So you could simply replace these with ReLU, and a Max. So this entire pattern, this entire architecture was what he called a neocognitron. Now, neocognitron obviously means that he earlier had another model that he called the cognitron. And this was the newer version of it. So this was the latest model he actually came up with. And now observe that all of this is based on the Hubel and Wiesel model, where you have S cells responding to outputs from the previous layer. And, oh, you got it. Thank you. And you have C cells. Ah, beautiful. You have S cells responding to the output of the previous layer, and then C cells responding to the S cells. So one of the characteristics over here, all of these are part of Fukushima's model, is that because these C cells are actually operating on groups of S cells, the C planes are smaller than the S planes. Their responses don't really overlap, which means the corresponding S planes are going to be just as large as the C planes, but the next C plane is going to be smaller than the S plane, and these things keep getting smaller and smaller. Also, as you go down here, the height of this plane keeps increasing, meaning if you have a certain number of S planes over here, S groups over here, the number of S groups out here is going to be larger than in the previous layer. And this keeps increasing as you go down the model. Fukushima also introduced a learning paradigm for this. So again, this is a computational model for the brain, right, based on Hubel and Wiesel. The learning model that he introduced was unsupervised, which means that there is no real target that's being provided. After all, when we begin learning, the human vision or animal vision has a very large unsupervised structure to it. We just sort of learn to make sense of the world, starting out as babies. So this was supposed to capture that. And he used the Hebbian learning formula. Now, we all remember what Hebbian learning was, right? You'd start off with some weights, and then each weight gets updated by the product of the input and output of the corresponding connection. So this is exactly what he did. He would randomly initialize the C cells, S cells, and perform Hebbian learning updates. And the way it would be is that for each, within any layer, so observe that you have all of these guys. You can just stack them up in one pile. And at this position, you would pick, this entire position is going to be responding to some corresponding region in the corresponding value in the previous layer. So you'd pick only the largest at that position and apply Hebbian learning for the corresponding weight, and then share it across all of the layers. We don't really need to get into the details of it, but the point was using this very simple mechanism of unsupervised learning, where he would initialize them randomly, then he would provide some inputs, and then within each S plane, for any value in the input, he would see which one fired most, and then update the corresponding weight using Hebbian learning. But then once you update the weight of one cell in a specific group, you'd update the weights of all of the other cells in exactly the same manner, because within each group, all of the cells are supposed to have the same response. And when he was done learning, he actually finds that any plane learns just one feature. So if you provided a network with lots of examples of the character A, for instance, then you would find that different planes would learn different structures of this kind in the first layer. Then in the next layer, they would actually get to begin learning more and more complex patterns. By the time you got all the way to the end, they would actually be responding to the character A. And he also showed that if you actually give it many different patterns, specifically he used digits. Now, this is what is seen by the retina. When you actually get to the third layer, you can see that when 0 is produced in his example, only this cell fires. When the input is 1, only this cell fires. When the input is 2, only this cell fires. So basically, in a completely unsupervised manner, this architecture learned to group inputs into different structures and to recognize different types of patterns, in this case digits. So it's a very nice model, which was completely biologically based. But then what is missing is supervision. And it's easy enough to just introduce supervision to this by using backpropagation. So the early models didn't have supervision, and various authors actually tried to introduce supervision to the whole process. Homer, Atlas, and Marx in 1988, they proposed using temporal correlations. Kevin Lang and Alex Weibel here in CMU came up with TD, time delay neural networks. All of these are variants of the same model. And at the same time, Jan LeCun in New York University came up with convolutional neural networks. All of these were basically parallel realizations of effectively the same idea. So here the idea is, instead of letting this final layer just learn patterns in an unsupervised manner, what I could do is pass the outputs of this final layer to yet another neuron over here and get a single class output and use that class output to go to backpropagate and train all of my neurons. So this is just the Fukushima model with one little extra stuck on at the end. And that is being used to train all the models. And this was Jan LeCun's idea. Again, the original principle is still being used. The original principle was that the C cells do not get updated. Only the S cells, which are plastic, are being updated. So you can see exactly where modern convolutional neural network architecture came from. There was no computational basis to it. The basis was entirely biological, based on Fukushima's original model, which itself was based on studies of cat vision, right? So again, note that the original neocognitron actually uses many identical copies of a neuron in each S plane. So over here, you'd have all of the cells in this plane are going to have exactly the same response. Same thing over here. All of the cells in this plane have exactly the same response. So in math, if I assume that the receptive fields of each of these cells is square rather than elliptical. Now in Fukushima's model, they were elliptical, but but it's easier to do this with square or rectangular responses. Then let's say the receptive field of any S cell is some KL cross KL, and for a C cell it's another square. Then what is really happening, then the actual computation you would be doing over here is that let's say these are the outputs of some C layer, and the subsequent S layer, this guy would use one set of rectangular weights for this corresponding S layer, C layer, a different set of rectangular weights for this one, so you get the idea. You'd have one set of weights for each plane, C plane, in the previous layer. And the actual response over here is computed by basically taking an inner product between these two guys and an inner product between these two guys and so on, and adding the whole lot up and passing them through a activation function. In this case, the activation function was just the sigmoid. And subsequently, of course, the C, again, the C plane is only going to be looking at, this is for a C, this is going to be looking at a rectangular block over here again, but the C plane doesn't look at the other S planes, and it just picks up the largest of the lot. So very simple idea. He just simplified the response of the various neurons, and then used backpropagation to just train the whole lot. So this was back in 1991 or 1990. And he actually showed that he could train this entire network to be recognizing handwritten digits pretty much in real time. So you can see the demo. This demo is still up on his website. And the US Postal Service actually used it for a while or so, I believe. So the story so far, the mammalian visual cortex contains S cells, which capture oriented visual patterns, and C cells, which perform a majority vote over groups of S cells. to account for noise and positional jitter. And the neocognitron basically emulates this behavior with planar banks of S and C cells with identical response to enable shift invariance. Only the S cells are learned, the C cells have a fixed response. And in the original model, unsupervised learning results it was shown that unsupervised learning results in the learning of useful patterns. LeCun's LayNet, that was LeCun's version of the model with the supervision, added external supervision to the neocognitron, where the S planes of cells with identical response are modeled by a scan. You don't need to have many copies of the same neuron. You can just take one pattern and scan. Computationally, they're exactly the same. And the C planes, similarly, are emulated by cells that perform a max over groups of S cells by reducing the size of the S cells. The entire structure was now the convolutional neural network that we saw in the last class. So here's the general architecture of the convolutional neural network. It comprises convolutional and downsampling layers. So these convolutional layers comprise neurons that scan the input for patterns. And then the downsampling layers perform max operations on groups of neurons from the convolutional layers. And although in the original neocognitron, each S plane was followed by a C plane, and then subsequently had another S plane that was followed by a C plane, and so on, when you actually begin performing computational models of this structure, there's no need for this alternating pattern. You could have any number of S planes followed by a C plane. The C planes could occur pretty much anywhere, right? So, and finally, when you have a number of these layers, the output of the final layer is actually passed through one or more layers of multilayer perceptrons to give you the final output. So this is just the simple, again, working our way backwards through history. This is just the simple Hubel and Wiesel model, which has been computationalized and supervision has been added to it. So we had this question in the last class: why do we need the max? Can we not just replace it with a standard convolution? You could. The max just happens to be there due to historical reasons, where it was shown that in the mammalian vision, this something very similar to the max operator permits positional allows us to account for noise and jitter, and so that has actually been incorporated into the CNN model itself. So here's how it would be: you'd have convolutions, downsample, convolution, downsample. You could have multiple convolutions following one another, and then more downsample. The convolutional layers and the MLP are learnable, the final MLP. The downsampling layers are generally not learnable. Questions? Yeah?
One question just from the previous lecture and from this one. In terms of back propagation, how do you back up through a max layer?
We're going to go through that, assuming I speak fast enough, right? Again, the convolutional layer, that's exactly this. The convolutional layer comprises a series of maps corresponding to S planes in the neocognitron. They're variously called feature maps or activation maps. So basically, these guys are feature maps or activation maps. What you're really getting is you're scanning the input for some pattern, and you get a map. So the pattern that you're scanning for is the feature that you're scanning for. The corresponding output is a feature map or an activation map. You'd have several of these. And this convolution is basically followed by an activation function. So what you have here is originally you're going to be looking at these inner products, and you'll be summing over, this is the inner product of these two guys. You'll be summing them over all the layers, and then you're going to put this through some kind of an activation. So you have the two-step process. First, you're scanning the input and computing these inner products, and then you're passing them through some activation. So these weights are what are going to be learnable. Now, when you go to any particular layer, all the maps in the previous layer are going to be contributing to the convolution for each position. So which means that exactly this. When I look at what this value is obtained by looking simultaneously at all of the layers and all of the planes in the previous layer, right? So now consider the contribution of a single map. What exactly does this convolution do? So just to give you an idea. So this guy is looking at all of these. Let's look at just what this one term actually contributes to the overall computation. Let's say I have a 5x5 image with binary pixel values. And this filter, let's assume that this term is 3x3. And you also always have a bias term, right? So basically, we're going to call each of these. So here's a little bit of terminology over here. These guys, we're going to call them filters. These weights, we're going to call them filters. You're going to be scanning the inputs with these filters, right? So when I scan the input with a image with a filter is really just a perceptron with weights and a bias. Here's what you're going to get. So let's say this is my 3x3 filter. I would initially just place this 3x3 filter on the top left corner. So it's these numbers in red are just showing the value of the filter. You perform a component by component multiplication. You add in the bias. The result is going to be a 4. And so you compute this, keep shifting this left to right, and you compute the entire map of outputs when you perform the convolution. So this output, so this is the scanning of the input with a filter. So we're basically calling the perceptrons filters. And then once done, that output is going to go through an activation, like a sigmoid or a ReLU. More in modern convolutional neural networks, we actually use ReLUs. So the actual processing is kind of better understood now, because I'm arranging all of these guys one below the other, that processing is sometimes not very clear to interpret. So this is a different illustration that actually is visually more meaningful is something like this. Instead of showing all of these guys one below the other, I can arrange them as a stacking, in which case this becomes a three-dimensional structure. So all of these planes arranged one behind the other can be thought of as a cube. And now my filter can be thought of also as a cube. And what I would really be doing is imposing this filter on the stack and basically performing a component-wise multiplication and adding the lot across all of these layers, and then adding in the bias. So this guy is going to be for just one map, right? I'd have many of these guys being computed, and then I'd scan around to generate the entire map, like so. So this is going to give me just one single map, meaning just one of these guys, and I'd have many of these within any one layer. So another thing that actually happens, just an engineering issue, is the way I've shown it. When I'm scanning left to right 1 pixel at a time. There's no necessity for you to be scanning 1 pixel at a time. You can actually be scanning the shift that you have is what is called a stride. And the stride could be more than 1 pixel. You could be jumping 2 pixels at a time or 4 pixels at a time. And the size of the output is going to depend on how much you jump between one position and the other. It's going to depend on the stride. So for completeness sake, let's just take a look at this. Let's say this original picture is 5x5. My filter is 3x3. So if I start from this position, after only 2 shifts, I run out of the picture, right? So the result is only going to be over here. It's going to be 3x3 because I can shift twice to the right, and then I begin moving out of the picture. So the complete map is going to be 3x3. So it would be something like this, right? Suppose I have a stride of 2 instead of a stride of 1. What would the output be over here? It's just going to be 2x2 because I jump 2 and then I'm done. So you'd have something of this kind. So in general, if my original image is n cross n and my filters are m cross m, the result is going to be that's right. This is going to be n minus m plus 1, right? Or in general, if I have a stride of s, that's going to be n minus m over s plus 1, the flow, right? You're going to be jumping around. The thing shrinks. So now what happens over here is that even if you just have a stride of 1, this results in a reduction in the size of the overall picture. And where you sometimes, in some conditions, this is considered unacceptable. You want the result of a scan to be the same as the size of the original picture itself. So in these cases, what you would try to do is to sort of pad the original image with zeros symmetrically, so that when you're done scanning, the resulting output is going to be the same as the size of the picture inside, right? And the way you would scan it, you're going to see how many columns you would lose, and you distribute that many columns evenly on both sides of the picture. So if your original image is n, the filter is m, then you're going to lose m minus 1 columns as you scan left to right. So you just distribute m minus 1 columns on either side. Similarly, you distribute m minus 1 rows on the top and the bottom and fill them up with zeros. So when you do this, if you have a stride of 1, the result of the convolution is going to be the same as the size of the original image. Now, we're calling it a convolution. The scan, this business of scanning with a filter is called convolution. But the term convolution itself has a very specific interpretation if you're a signal processing person. Now, keep in mind again, that just taking some pattern and scanning, as we saw, that is convolution. But it turns out that when I think of that, instead of actually scanning things in this manner, I can perform the exact same computation in a slightly different way, in a transform domain, and actually save significantly on the computation. So the question goes back again to, why should I be scanning with each MLP individually instead of just scanning with my entire network? Go back to what we said in the last class. This entire business of scanning was exactly the same as composing a multilayer perceptron with different kinds of neurons and with your parameter sharing properly defined, and scanning with the entire multilayer perceptron, right? What is the need for actually changing the order of computation? It's mostly for efficiency. Now, when you scan things, right, in terms of matrix operations and such like, it tends to be much more efficient. It's also kind of somewhat more intuitive. There's also the other fact that I can do it using Fourier transforms. Now, what happens is, let's go back here. If I'm scanning an image, which is m cross m, with a filter that's n cross n, how many computations do I really have to perform? At each position, I must perform n squared multiplications. That's just for one position. And then I'm scanning m cross m times. So the total number of computations is going to be order m squared n squared. Whereas if I do it in the Fourier transform domain, if I do this with Fourier transform, it turns out you can just do it in order m squared log n. And for large filters, this can actually be a significant saving in terms of computation. Also, if you're doing this many, many times, then this can actually be a significant saving in computation. But again, these are just the mechanics of it. The point is, the act of scanning is convolution, and it can be done in different ways. And it's computationally efficient to think of it as scanning with individual filters as opposed to scanning with an entire network. Right? So here's what we're going to get. The convolution operator results in a convolution map. So I have this entire layer. I'm going to use a filter. That filter operates on this collection of maps. And so you're going to get a single map for each filter. And the output of the filter is going to go through an activation. And wait, why am I? And these outputs are then subsequently passed through these so-called downsampling layers. What exactly are the downsampling layers? Again, this is something that we've seen in the last class. So let's say this downsampled output is going to be obtained from this map over here using a very simple operation. You're going to be looking at groups of neurons and just picking the largest value. So let's say these values were 3, 1, 4, and 6. The largest of these is 6. That's the only thing that you would pick. So as you kept scanning left to right, you'd be looking at the current set of the map values, picking the largest one, and copying that over till you created the entire map. And once again, over here, you can stride by more than one, right? And striding by more than one is going to result in a reduction in the size. And typically, when you're performing the max pooling operation, you are going to be striding by more than one, which is why we call this the downsampling operation. So if you have some p cross p pooling and you have some stride d, the result is going to be n minus p over d plus 1, exactly the same as we saw before. So you don't always have to take a max. There are other operations you could perform. So instead of just looking at picking the maximum of these guys, you could be picking the mean. Remember, the whole business of taking the max was to permit a certain amount of jitter in the input. Taking the mean might also give you some amount of jitter invariance. The advantage of the mean over taking the max goes back to Andrew's question, how do I actually take a derivative? In the case of a derivative, it's fairly in the case of a mean, it's fairly obvious. In the case of a max, it's not clear how you take a derivative. Or you can take something like the p norm. And the max is actually a limiting case of the p norm. So you can perform different operations. Or even you can replace that entire operation with a little multi-layer perceptron. So instead of actually performing a max, you can actually learn what the operation might be. And that learned operation could be a single perceptron, or it could be a multi-layer perceptron, or it could be anything of that kind. Again, the point is this operation is being performed by scanning over the input. And it turns out that all of these different variations have been proposed in the literature. And there are different papers about it. So, which means that I can get rid of the max altogether and just have only convolutions, where downsampling happens in some layers which have strides greater than 1. And this is the so-called famous all-convolutional network, which is what people mostly use these days. The entire business of using a max that can be dispensed with, because it's just an artifact of trying to emulate the operations of the human eye, and there's nothing magical about it. The max is just an operator that could be replaced by pretty much any other operator, including just a standard convolutional layer with a stride greater than 1, right? So here's the story so far. The convolutional network is a supervised version of the computational model of mammalian vision. It has convolutional layers comprising learned filters that scan the outputs of the previous layer. You have downsampling layers that vote over groups of outputs from the convolutional layer. And the convolution can change the size of the output, which you can control by zero padding. And downsampling layers could be performed using maxes, means, p norms, or just learned downsampling networks. And downsampling can also be performed using just regular convolutional layers with a stride greater than 1. Right? All of these are feasible. So let's put all of these pieces together, right? Let's take a typical image classification task, and I'm going to assume max pooling because it's the historically what's done. So your typical image is going to look something like this. You'd have a color image. There's a corresponding grayscale image, but the color image actually comprises 3 different images, an R, a G, and a B, right? So I can stack so here's the input. I can stack the 3 together, and I can think of my image as a cube to begin with. So typically, engineering, you work with square images. Filters also typically tend to be square because large networks are a problem. Those of you who will be doing this homework will realize pretty soon that if the input gets too large or the filters get too large, you're going to run out of memory. So originally what people would do is to scale these images down to really small pictures, like 32 cross 32 or 128 cross 128. These days we can actually work with larger inputs. So here's your original input. You're going to define a bunch of filters, some k1 of these. Each of these is going to be a cube, right? And these filters would, the filter sizes are typically 5 cross 5, 3 cross 3, or even 1 cross 1. And the number of filters is typically set to be a power of 2. Again, I'm giving you values that have historically been found to be kind of effective. But there's really no, I mean, there's nothing magical about powers of 2. These are just typical values, right? Now, what exactly is this 1 cross 1 filter? We all understand what a 3 cross 3 filter is. What would a 1 cross 1 filter be? So it turns out a 1 cross 1 filter is just a perceptron, a simple perceptron that's looking across the planes. Instead of looking at groups of outputs, it's looking at one single pixel across the planes and scanning the entire input. So even 1x1 perceptrons filters are quite commonly used. So here's what we get. You get an input that's convolved with a set of K1 filters. And here's a better notation. I'm going to say, instead of 5x5, I'm going to say 5x5x3 to indicate the fact that here there are actually 3 planes stacked one above the other, right? So the filter is actually a cube. That's what this represents. A 3x3x3 means that it's 3x3 spatially, and it's got a depth of 3. Or even a 1x1 is actually a 1x1x3. It's got a depth of 3, right? So how many parameters would we have in all? If I have K1 filters, and if I have a depth of 3, and if each filter is L cross L, I'm going to have K1 times 3L squared parameters. Strides are typically 1 or 2. So I scan these, and depending on whether I really want the size of the output to change or not, I may or may not pad with zeros. Once I scan it, I'm going to get a bunch of outputs. The actual scanning is computed in this manner. And for each of these filters, at each position, I can compute the z value, which is obtained by simply placing this filter on the corresponding location and taking an inner product between the filter and the input itself. And then the actual output is obtained by applying an activation to these z values. So you'd get a bunch of outputs, right? So for the first layer alone, you're going to have K1 times 3L squared plus 1 parameters, where the plus 1 is meant to account for the bias. Then subsequently, you're going to have a max pooling operation. Now, getting back to Andrew's question, exactly how am I going to think about the max pooling? The output of, I'm going to have some map over here that I have computed, and this location is the max of all of these guys. I will think of it as a 2-step process. In the first step, I find out which position was the max. So that is the P, that is the U over here. Where did that go? That is the P over here. And then subsequently, I'm going to read the value at that position. So I'm thinking of this as a 2-step process, and we'll see why this matters. So here is the result of the first pooling layer. Again, I've stacked all of these things together, and now again, I can think of it as a cube. At the next level, again, I'm going to have some K2 filters, but each of these filters is now going to be L2 cross L2, because whatever this L2 might be, which is the size of the filter. But the third dimension is K1, which was the number of filters in the first layer. So when I think of this cube, the depth is the number of filters in the first layer, because that's how many of these guys I would find. And these outputs are then subsequently also shrunk down using a max pooling layer. So over here, the number of parameters is going to be K1 L squared times K2, because K1 is the depth as opposed to 3, right? And then I'd have more downsampling. And once again, in the case of the downsampling, there are more parameters to choose. What is the block over which I'm actually computing the max? And what is the stride? In each case, these are all parameters to be chosen. After several layers of these, the final output would be flattened out and passed through a multi-layer perceptron to get your final classification. So if you think of the size of the layers, each convolution layer, if you zero pad it, it's going to maintain the size of the image. Without zero padding, it would shrink it. Now, in each convolution layers, what's going here? Let me turn this off. So within each convolution layer, I can actually increase the number of maps. So in the first layer, I might have some K1 filters. In the next one, K2 can be greater than K1. And the next layer, K3 can be greater than K2. And this is typically what is done. As you go through the layers, because as you keep downsampling, the size of the maps keeps shrinking, but the number of maps keeps increasing. And typically, each layer, it's popular to make each layer some power of 2 deeper than the previous layer, which means that if the first layer has 4 filters, you like to have 8 or 16 filters in the next layer, 32 or 64 filters in the next layer, and so on. You like to increase the filters in terms of powers of 2. And the final MLP, you have to decide how many layers and the number of neurons in each layer. The numbers are on the slides, partly. I'll skip the details. So here is the kind of structure that LeCun originally had in his original paper. His inputs were all 32 cross 32 inputs. His filters were 5 cross 5. And he didn't zero pad. So once you're done operating on a 32 cross 32 image with a 5 cross 5 filter, the result is 28 cross 28. If you downsample by a factor of 2, which is to say you're taking a max over groups of 4 inputs, that's going to become 14 cross 14. And then he had more 5 cross 5 filters. So these become 10 cross 10 maps. But then the number of maps is, here there were 6, here there are a much larger number. They shrunk by a factor of 2, and then eventually he had a bunch of neurons in his MLP. So we've defined this network. How exactly do you perform the learning? The learning can be done using conventional backprop. Again, this is just straightforward computation, right? So for this guy, you have to learn the weights and the biases for the final MLP, but you also have to learn all of these filters and their corresponding biases. So here's what we can do. The training is just as in the case of a regular MLP. The only difference is in the structure of the network. So you'd have some training examples, images and their class labels, exactly as before. You'd define a divergence between the desired output and the true output of the network. And the network parameters are trained using backprop. So for this final MLP, the backprop is performed exactly as we would in the case of multi-layer perceptrons. And eventually, out here, you are going to get the derivative of the divergence of the output with respect to all of these inputs. From there on, you have to perform backpropagation all over again. And there are 2 key pieces. Here, we need to make some adjustments. Firstly, we have to worry about how to propagate gradients past the max pooling layer. The second, we have to worry about how convolution itself, the sharing of parameters in convolution, affects the derivatives. So let's consider the max pooling. I just have this in symbols, but when you're performing your operations forward, at each location, you keep the value or the identity of the location from which you pick the maximum value. Now, what exactly does a derivative mean? A derivative tells you how much changing a specific value is going to change the output. If I only copied this value to the output, then changing the rest of these guys is not going to change the output. So you'd set all of the rest of these derivatives to 0, and you're going to set the derivative of the one guy, which is the maximum, to be the derivative at this point. So the derivative of the divergence with respect to this term is going to be the same as the derivative of the divergence with respect to this guy. For the rest of them, it's 0. So straightforward, right? That's how you actually propagate your gradients to the maximum. Make sense?
The one question I have is, that derivative will hold until the other weights change to a point where they become the max.
Now, this is an approximation. So because...
Okay, so it is approximation.
Yeah.
Right. So it's within a certain range.
It's a subgradient. It's not really a gradient. But
So it's close to the point where we're at.
Yeah.
Okay.
typically, the rest of them are going to be far enough away. Remember, you're speaking of really infinitesimal changes, the effect of infinitesimal changes to these values on the output, right?
Yes.
And if the difference is, anything greater than negligible, then those derivatives really will be 0. Right? So now what about the weights? So it turns out that each weight contributes to every position in the map at the output of the convolution layer. So if you actually look at this guy, this weight, this location has contributions from all of these weights, but these weights also contribute to every single position, right? So if I want to compute the derivative of the divergence with respect to this one weight, I have to compute the derivative of the divergence with respect to every position in this map, and then compute the derivative from here to this corresponding weight, and then add them all up. So the result is that when you actually look at, so just to explain what I mean, think of this filter. Let's just look at the top left corner, right? What we are really doing is scanning. And when you're scanning, basically this guy at the corner is affecting every single output. So if you want to see what the derivative of the weight at this corner, what the derivative of the divergence with respect to the weight at this corner is, you'd have to sum over all of the terms that that particular weight actually affects. And so that's going to have a fairly ugly formula, which I'm actually not going to explain. But if you look over the slides, it makes sense, in the sense that what we are really doing is we are summing over all of the positions, and within each position you are summing, this is the derivative, this is the derivative of the divergence with respect to the output of the activation. This is the derivative of the activation itself, and this is the derivative of the z value with respect to the weight, which is simply the corresponding input, which is the output of the previous layer, right? You're summing over the entire map. The same thing happens when you're actually trying to compute how changing this one guy changes the divergence. Changing this one guy is going to do something, or say, is going to do something very interesting. It's going to change every value out here, but it's also going to change every value in the next plane, and the next plane, and the next plane, and the next plane, and so on. So you'd be summing over all of these and summing over all planes. So as a result, you have multiple summations. The first one is summing over the entire plane for each of the planes, and then summing over all of the planes. So it's just a simple modification of your standard backprop, right? You're just accounting, if you actually draw the influence diagrams, you can actually see everything that is being affected and add them all up. So this entire gradient computation can now be embedded into a standard backpropagation and gradient descent algorithm. I've sort of skimmed over all of the details, but then the concepts are fairly straightforward. There's nothing particularly dramatic about any of this. The only novelty over here is the shared parameter structure and the scanning. So here's the story so far. In summary, the ConNet is a supervised version of a computational model of mammalian vision, which includes convolutional layers, which comprise learned filters that scan the outputs of the previous layer, and downsampling layers that operate over groups of outputs from the convolutional layer to reduce not the network, but the output size. And the parameters of the network can be learned through regular backpropagation. Max pooling layers must propagate derivatives only over the maximum element in the pool. And for the rest of them, the derivatives must sum over appropriate set of elements to account for the fact that the network is, in fact, a shared parameter network, right? So training, standard convergence issues. If you worked on homework 1, you know exactly how you're struggling in making things converge. You typically need things like RMS prop and other momentum style algorithms. The number of parameters can quickly become very large, which means that you're going to end up with insufficient data. And here's where you actually take advantage of the fact that you're actually looking for repetitive patterns. So there's a very standard approach for augmenting your data, which is to start off with the original data and perturb it, like rotate it, stretch it, distort it in a little way, and make synthetic data. And you can actually increase the volume of training data by many orders of magnitude in order to increase the effective amount of training data that you actually use. There are details of the different kinds of transformations you can perform are on the slide. So also, when the networks, you can have any number of convolutional layers. And as you increase the number of convolutional layers, the effective performance, the effectiveness of the network can be expected to improve because you are be able to search for more and more complex patterns. But then now you run into training issues, as we will see in a later class. When the number of layers becomes very large, then the gradients get really unstable. So to account for this, one of the most common formalisms is something called a ResNet, which we'll see in a few minutes. So convnets are currently probably the most frequently used formalism in computer vision and speech, in many, even language. So these things are well worth learning about. They're used pretty much everywhere, right? Let's look at some typical examples of successes. We saw this for digit recognition. This was Jan LeCun's original LayNet back in 1990. And this was, I'll skip this. These were things that she computed for me. Right. So what exactly, first a little aside, what exactly are the patterns that each of these neurons are looking for? Maybe you can explain? No? She computed them for me, that's why. So remember, we have all of these filters. Every filter is just a correlation filter, which is looking for very specific patterns. So in the digit recognition task, after you've trained this, how many layers did you have over here? Don't remember? So the first layer, if you look at the patterns that the filters in the first layer are looking for, here are some patches. As you go down the layers, you see something very interesting. They actually eventually begin looking like digits. So we can actually see that the filters in the final layer, if you look at the kinds of patterns in the input that they're actually responding to, they actually end up looking like digits. And this is for a digit recognition task. So this kind of entirely makes sense, right? So now let's go back and see how many parameters these networks can have. Jan LeCun's original LayNet for MNIST had 6 filters in the first layer. Each was 5 cross 5. So you have 6 times 25 parameters. Then he had a 2 cross 2 pooling layer with a stride of 2. Then the next one, he had 16 5 cross 5 filters. And then after downsampling, it becomes 10 cross 10. Then subsequently, he had 16 more 5 cross 5 filters. And the final MLP had 3 layers. So it's a fairly small network. But now, here's something much more interesting. People had been working on convnets. They were very familiar with convnets for the better part of 20 years. And they didn't really become very popular till the ImageNet task, till they began trying this on ImageNet. Now, ImageNet is this task that was defined by Fei-Fei Li in about 10 years ago, which includes millions of images and thousands of categories that have been downloaded from the web. And the task is to be able to classify these images into categories like a mammal, a placental mammal, a carnivore, a sailing vessel, a sailboat, and so on. And they actually set up an official evaluation where they chose 1,000 categories of images. And for the first several years, the performance was pretty poor. Then I think this was in 2012, Krzyzewski, Sutskever, and Hinton came up with this breakthrough. They came up with a very complicated convolutional network. The network was so complicated that they couldn't even print a diagram of it on their paper. And so when they finished printing it, they had to chop off the upper half. As you can see, this is from the paper. And this network contains 60 million parameters and 650,000 neurons. 5 convolutional layers, some of which were followed by max pooling layers, and finally 3 fully connected layers. The network was so large they had to distribute it over 2 GPUs, which is why you have 2 2 blocks over here. So the inputs were all scaled to 227 cross 227, and you have RGB, so 3 images, right? Then the first layer had 96 11 cross 11 filters. Then you had a 3 cross 3 filters, pooling layers with a stride of 2. Then you had 256 5 cross 5 filters, and then pooling over 3 cross 3. Then you had 384 3 cross 3 filters. Then you had 384 more 3 cross 3 filters. And then you had 256 more 3 cross 3 filters. And then you had fully connected layers. And when everything was said and done, you had 650,000 neurons, 60 million parameters, 630 million connections. Many of them are shared. And that wasn't done. Once they actually trained the network, when they actually performed classification, they wouldn't just give it the original image. They would sort of shift the image around, basically crop different sections of the image, and perform classification many, many times, and then vote over the lot. So they have some more details of the training in their paper, but here is the key piece. Right before their paper, the error rate on classification error rate, top 5 classification error rate on ImageNet was greater than 25%. With their ConNet, that suddenly went down to 18%. And when they used 7 of these networks and voted across the 7, the error went down to 15.4%. So that's like a 40% reduction that they got in one paper. This was obviously a landmark paper, right? And they also showed, here are some examples of the kinds of filters they actually end up learning in the first layer. But more interesting was this. Here are some outputs that they got. This is being recognized as a mite, a container ship, a motor scooter, a leopard. This is actually being recognized as a cherry, although it's supposed to be a Dalmatian. But it's got cherries, right? This is a squirrel monkey. It's being recognized as a Madagascar cat. And this is very validly being recognized as a mushroom. But I don't know why they call this a grill. But even the misclassifications were very often not totally off. And more interestingly, they found that when you actually have the ConNet, you can take the representation that the final layer gets and treat that as a feature. And if you just computed the features from many images, so in this column, they use the features derived from these images as queries and try to find other images whose features are closest to this one's features in an inner product sense. And they find that the flower actually pulls up other flowers. Elephants pull up other elephants. So they also found out that they're automatically learning very meaningful kind of features, right?
What sort of inner product did they use? Like, is it just like
Just standard cosine distance over here, right? Then things go haywire. So Zeiler and Fergus, they engineered that down. They reduced the number of filters. They reduced the size of the filters. They reduced the size of the filters, made it simpler, increased the number of filters. They brought the 15.4% error down to 14.8. And then these guys, they are the best. They ran, this is a classic case of stochastic research, right? They took, they literally ran thousands of different configurations of ConNets. I'm not sure exactly where they got all the GPUs for it, but just this one experiment must have increased the global temperature by 1 degree centigrade, right? And finally found that with a network with 140 million parameters, they can bring the error rate down to 7.3%. Now remember, you're speaking of something that was 25% only 2 years earlier, right? And so VGGNet remains one of the most popular models that people use for ImageNet these days, and you can download it off the web. And then Google went one step crazier. They came up with this really crazy architecture that I can't even explain. The nice thing is it has only 5 million parameters, and now the error rate is down to 6.7%. And then the Microsoft guys went off again, and they increased the number of layers, but then they have one extra trick that you guys are likely to use, and maybe you will actually see in your recitation, which is the ResNet, where after 2 convolutions, they take, or after a certain number of convolutions, they add the output back to the input. So this has the nice characteristic of not having the derivatives blow up or shrink to nothing as you go down very deep networks. And now you can have networks with thousands of layers. And as a result, the error, which was 25% only a few years ago, is down to 3.5%. And the latest errors are like, more details, right? The latest, and now a couple of years ago, there was an award-winning paper called the DenseNet, where this was, again, the way to think about it is, again, you're scanning the input with a multi-layer perceptron, but it's not really just it's not a multi-layer perceptron in the traditional sense. They have the initial layer, but instead of, then you have the next layer, which is fed by this layer. But the next layer is fed by both these guys and these guys. And then the next layer is fed by these guys, and these guys. You just keep accumulating connections as you go down the network. And the number of parameters becomes very large. And that was the state of the art before I went for coffee, a couple of years ago. And I came back, there was a new paper on arXiv with better architecture. So they keep updating this stuff. But the point is, if you actually follow the literature in CVPR, every 3 months they come up with a modified version of ConvNets, but the basic idea remains the same. You're scanning the input. The only thing that's changing is the configuration of the network. And these things are ridiculously effective. You're going to be using them for speech in homework too. And you'll find out all about it in your homework, so I'm not going to talk about it. So anyway, I'll stop here. With apologies for lots of stuttering and stammering. I'm still jet lagged. But here's the summary. A neural network with specialized connectivity structure. That's what a CNN is. It's feed forward. The input is processed in a convolutional manner. You have a standard nonlinearity pooling. That's the structure. The training is supervised and is done through backpropagation.